Hello, am I audible?
Yes, you are audible.
Okay, sure. Uh, okay, it seems Professor Gupta has also joined today's session. So thank you so much, sir, for joining today's session. Uh, actually, we will wait for some time for some more few people to join. Then we can start the session. So, is that fine, sir?
Absolutely.
Thank you, sir. Okay then. So we have waited for some while, but it seems that other students have not joined yet. So it's okay. And again, I apologize that I have been a bit late, 2 3 minutes late exactly. So I'm sorry for that. And welcome again to the third week of the problem solving session of the course Fluid Mechanics and its Applications. So um, and I okay so okay so actually I didn't expect that Professor Gupta will also join today's session, so uh, I am quite uh, exhilarated and quite surprised, I might say, but that's fine. I'm very grateful Professor Gupta has found time to join the session, and we welcome him. And since only one session is one student is there, Alex, so I feel it's fine to start the session. So okay, so in this week's session, we will be discussing about flow description, or which are the methodologies or ways by which flow can be described or visualized. Means like up till now we have seen various flow properties and how they are measured by the help of various gauges, manometers, piezometers. We have looked upon such equipments, and so but now in this session we will be extensively discussing about how the flow can be described mathematically, or what are the terminologies or methodologies by which flow can be described in a mathematical manner. So that's our goal. And also uh, as we all know, fluid mechanics in its very core is a highly mathematical subject. Like, it was initially being designed by mathematicians, and the very foundations of fluid mechanics has been laid down by mathematicians. So uh, the exact or the true approach of understanding the true fundamentals of fluid mechanics are by the help of mathematics itself. So that's why we will dealing with some mathematics and how these mathematical equations, at least in the later part of the course, we will see how these mathematical equations uh, express themselves and helps us to understand the physics of the flow. So that will be our agenda. So okay, so in as described by Professor Gupta, the learning outcomes from today's session would be we will briefly discuss about the Eulerian and the Lagrangian description of the flow, and also know about how to measure the time rate of change of properties or the flow properties. So like velocity, pressure, we will discuss about that, and that's it. So now, okay, so before discussing that, there's a very important topic to be, I must say, clarified, or at least be clear about before handling the mathematics of the mathematics that are being implemented in fluid mechanics. So as we all know, for any function to be derivable or differentiable, it has to be continuous. And since, as we will eventually see, that we were going to deal the flow properties as functions, in mathematical functions in this case, and we will be finding out a derivative of, as rightly mentioned here, the time rate of change of properties. So we will be basically dealing with time derivatives of flow properties. So for this time derivative to exist, the flow properties must be continuous. And you will eventually see that the time derivative does not only imply derivative with respect to time. There is a concept of material derivative or total derivative, which in its essence also includes the local time derivative as well as the the convective derivative or the change or convective derivative basically tells us gives us a quantitative value of the change in the properties because of the because of a change in the what to say through the space coordinates, because of a change of the properties through the space coordinates. So we will see that's why the total derivative in its essence is a function of both space and time. So, and we'll eventually see how the concept of a fluid property being dependent on space and time comes into picture. So we will eventually discuss about it. And here I will just try to discuss a bit about notation here. This notation here, you might see that I have put the vector sign, the arrow in below x. So this is notation that I usually use. So it's completely fine, like if you denote the x vectors as this. But for my comfort or for my ease of writing and understanding, I usually prefer to write the vector sign below x. So I guess that will be fine. So just that nobody is confused. So that's why I am mentioning my notations. So I guess that's fine. Okay. So before discussing about the concept of continuum, I believe Alex must have you must have looked into the lectures of Professor Gupta, who have extensively discussed about the concept of continuum. So okay, I will hide this diagram right now. So just as much as you can recall, can you please tell me what do you understand by the concept of continuum or the continuum hypothesis as it is also known? Alex, so you can please unmute yourself. Can you please tell us about the concept of continuum and let us know like what you have learned about it? Am I audible, Alex? Yes, Alex, you are in the class, so I kindly insist you that you unmute yourself and just share something about what you have learned about the continuum hypothesis. Oh, no. That's fine. Please, that's fine. That's completely fine. Learning about something beyond your area of specialization is completely fine. And no, that's fine. Please, please unmute yourself and speak up. Like whatever you have listened to read, just at least I can then try to explain whatever you're going to tell, or correct whatever you're going to tell. Okay, so now we have Shivendra also. So welcome Shivendra for the week 3 session. So since you have joined a bit late, we were discussing about the continuum hypothesis, which was, I guess, extensively discussed by Professor Gupta in the lectures. So could you please tell us a bit about what you have learned about the continuum hypothesis, or why it is important in the first place? Okay, so that's fine. That's completely fine, no issues. So because of I must say, because of the time limitation, I won't go through extensively through what the hypothesis actually means, since there's a lot to explain, and if you go on to explain it, it will take a lot of time. But just to get a gist of it, we can express it as the way or the manner in which we choose our smallest time scale, smallest length scale in the flow field to calculate or evaluate our flow properties, right? See, in some sense, you can see here in this equation, the density of the fluid can be described as the mass per unit volume, right? So the question comes, like, whatever may be the size we choose of our fluid particle, it would have a certain mass. That's for certain. There's no issue in that. But the main question comes that what must be the size of this volume, that what must be the length scale of this volume, right? Because you may say that based on our understanding of mathematics or derivatives, we can say that we see that, like, if in the case of if we're going to find out a derivative of a function, like basically the rate of change of one variable in terms of other, then we say that say dy by dx, if you're trying to find basically a slope, if it is a curve of y by x, say, then we basically say that for limit delta x tends to 0, we try to find the change of y with respect to x, and when we say that this delta x tends to 0, means it's very small, right? And if we go in that line, we may say that delta v should tend to 0, right? It should be very small, it should almost tend to 0, so that we can find a very accurate value of our density, right? But as discussed in the lectures, you may have, we see that when we are dealing with very small length scales, like extremely small length scales, we see that we encounter high fluctuations in the value of density, right? Because the length scale is so small, and because the length scale which is so small that the flow property, basically the density changes abruptly from point to point, because the length scale is chosen is so small, and thus its value varies from point to point abruptly, and thus we don't get a constant or a constant value or a regular value that we are expected to get, right? We are expected to get. See, both Alex and Shivendra, if I am not wrong, yes, both Alex and Shivendra, since there are only 2 students in the today's session, I insist that if you have any doubt in any line, you can please ask me. And moreover, we are very fortunate that Professor Gupta has also joined today's session. So if you have any doubt, you can please stop and ask both of us, and especially Professor Gupta. If I am saying anything wrong, you can please correct me at that moment. So I will be very grateful. So this is what I just wanted to convey. Okay, so I guess both Alex and Shivendra know what I wanted to speak about. So yeah. So again, so that is the issue with choosing very small length scales, like very small length scales. You will get very abrupt change in the values of the property. In this case, density. Now again, you may say that since choosing very small length scales is not good, then let's choose very large length scales, right? Large length scales, so that we are not encountering the issues of this abrupt change in properties. So now you say that let us choose large length scales. Let the volume be very large, say 1 meter cube. Then again we see that now if we take very large volumes, or the length scale of this elemental volume to be very large, then we see that we are not able to capture the smooth, or we are not able to capture the changes in properties that might occur, which have length scales that is smaller than our chosen length scale. Okay, so it might happen that, say, I will not take the example of density. I can take the example of density, but say for I will take an example that makes you understand it very clearly. Say we are now trying to understand the yes, I will write it here. So say we are trying to understand the flow physics of flow around an airfoil. Okay, so we are discussing about flow around an airfoil. This is I guess this the topic of flow around an airfoil we have discussed a bit in our previous sessions, so I think all of you are quite aware about it. So we see that near the surface of the airfoil there is some flow acceleration, so I will denote it by red. So you can see there are high values of velocity at the upper surface, and then we see that gradually these velocities gradually reach the value of the free stream velocity. Please ignore the length of the vectors. So just to just to conserve the space, I have chosen these vectors to be very small, so kindly ignore that. So sorry. Yes. So again, we'll see that from the suction side also, or the lower part of the airfoil. Sorry, pressure side also, you can see that the velocities gradually reach up to the free stream velocity. Okay. Here, because of the shape in this region, draw a buffer region. Say in this buffer region, say you will have u greater than u infinity. Okay. And this this increase in velocity is because of the curvature. So let's not dive deep into that. Let's separate topic, and we see that gradually as we go up or move away from the airfoil, the velocity will diminish, reduce a bit, and reach up to the free stream velocity. So that's certain. But now see, this change in velocity from the surface of the airfoil to the free stream, or up to a certain distance, say capital L, should happen gradually, right? Just as we say that for a function to be derivable, we expect the function to be smooth, right? We don't expect the function to have sharp edges, right? Implying the similar concept here, we want that the velocity should vary gradually from the surface of the airfoil to the free stream, right? There should be a gradual decrease in the velocity, or the variation in velocity from the surface of the airfoil to the free stream. And but say if someone has chosen, if you are trying to find the velocity gradient, say dv by dy, I will not say v, let's say u, since that's a dominant velocity. Say we are trying to find dou u by dou y in this case, right? The variation of the u velocity component with respect to the y coordinate. So this is our coordinate system. So if someone chooses a length scale, say around L equal to, say 3 meters, say. So if his unit length, or the smallest length scale that he have chosen for his measurement is 3 meters, and say the length of the airfoil is 1 meter, the chord length is 1 meter, say. So let me say it's 1 meter. Then what would happen is that, say if he is choosing since his smallest length scale is 3 meters, he will get a velocity at the distance. Say if his initial measurement is at the surface of the airfoil, say here near the surface of the airfoil, say at this point 0.1. So his second point would be at a distance 3 meter from his initial point, right? So the point 2 would be around 3 meter. It would be 3 meter away from the point 1. So the velocity that he would get at this point would be I will not say highly, but considerably different from the velocity at point 1. So you can you may see that you will not get a smooth transition in velocity from point 1 to point 2, and instead you will get some discrete value of velocity because of your chosen length scale. So that's why, as implied here in the definition, at the same time the length scale should be small enough so that the macroscopic variations are not smothered out. Smothered out means not erased out or not neglected. Okay, so that should be our ideal choice of our length scale that we choose for measuring the our flow properties, or at least find length scale for with respect to which we find a variation of our flow properties in our flow domain. Okay, I hope it was clear. So that's fine. Regarding that, similar to this definition, I will just read it out once again. That the measuring length scale that we choose for our flow property should be large enough so that only an aggregate effect of the molecular interaction is reflected. An aggregate effect, because if we choose a very small length scale, it will give the value of our flow properties at discrete points that would change abruptly. Okay, if it's very small, so it should be like that it shows an aggregate effect. Okay, of an aggregate effect of the flow property at that certain location. So that's with our chosen, the size of our chosen length scale. But at the same time, it should be small enough so that the macroscopic variations are not smothered out. Okay, so I guess definition is quite clear, and example is also, I think it was satisfactory. But if you have any doubt, you can just stop me at that moment. Okay, so adhering to the definition, it is how a choice of fluid particle is defined. A fluid particle is defined. So we see that a fluid particle of the fluid in the continuum model is an aggregate of molecules which within a small volume, which is large enough so that only an aggregate effect of the molecular interaction is reflected in the measurements, but which at the same time is small enough so that the macroscopic variations are not smothered out. Okay. In the first or in the initial stages, it's very difficult to visualize the fluid particle, and one may also eventually in the initial stage may confuse a fluid particle with fluid molecule. Okay, but I just want to emphasize that a fluid particle would be much larger than the molecule of a water, of your particular fluid. Say if it is water, then the water, it will be much larger than the single molecule of water. Okay, so this is how the length scale of a fluid particle is compared to a fluid molecule. It will be much larger, or in some sense you can say it will be aggregate of lots of water molecules. Okay, so in line with what we are discussing, there is another concept, or I must say way in which you can also you can also understand or quantify your understanding of continuum hypothesis. So there is a non-dimensional number. This is, I guess, this will be the second non-dimensional number after a Reynolds number that we are going to deal with. So this is known as Knudsen number. Okay, denoted by Kn, denoted as Kn, which is the ratio of the mean free path of the fluid particles with respect to the characteristic length scale. Okay, it's fine if you don't understand all the terms, but just for your understanding, I am trying to define it. Where we denote the mean free path length as lambda and the characteristic length scale as L, or in some sense you can also write as LC. That's completely fine. Okay. So here the mean free path basically means that the smallest distance or distance that the fluid molecule traverses. A fluid molecule traverses in the fluid flow domain before encountering or colliding with the next fluid particle. I'm sorry, not fluid molecule, fluid particle. Okay, so that's the mean free path. Mean free path, the free path or the distance, the free distance up to which it can travel before colliding or interacting with next fluid particle. Okay, and then the characteristic length scale in a proper definition is the length scale along which we can observe a considerable change in the fluid flow properties. Okay, that is a characteristic length scale. So right now I don't feel it's a good time to give you a proper understanding or proper examples of characteristic length scale, but just to let you know, there is a term known as characteristic length scale, and it is a length scale along which we can see or observe a considerable change in the flow properties. Okay, we will eventually discuss it in the later stages of the course. So it's a very important tool in having having an engineering perspective of this course, like how an engineer would visualize these courses, so it helps to understand them. Okay, so I hope I was able to clarify. So this is also one of the ways in which you can quantify the continuum hypothesis. So if I'm not wrong, I may be wrong. I will just clarify in the next session if you allow. The Knudsen number should vary, I guess, from 0.01 to 0.1 for the continuum hypothesis to be valid. So I may be wrong in the ranges, so it may be 0.001. So I will just check it before coming to the next session. So this is the value of the Knudsen number. The Knudsen number should vary in this range so that our continuum hypothesis is valid. Okay. So just kindly forgive me for the ranges. I was not. I'm sorry that I was not properly revised it before coming to today's session. So I will check it before coming to next session. So I will clarify it. Okay. Okay, then there comes the concept of field. As we were discussing that we were going to deal with the mathematical, we'll try to understand or visualize our flow field in a mathematical manner. So for that we will be dealing with functions, right? And if we are dealing with functions, you understand that these functions are defined within certain domain or field, right? And for a field, let's just hide it. So just before discussing our field, could any one of you please, whoever is present here, let me see. Okay, both George and Alex and Shivendra is available. So could any one of you please tell me a very vague or very simple definition of field, like what do you understand by field? So Alex, in electrical engineering also, I believe we deal with the concept of field. So based on that, could you please explain me what a field is? Just a crude definition. You can write it also. There's no issues. Shivendra, Alex, any one of you please, could you please define what is field? So what is a field? Just a very vague, simple definition. I don't need the exact one. Okay, Alex, since you mentioned that you are from electrical engineering, so or deal with it is a concept of electrics, so electrical engineering. Could you please tell me, define electric field? Like, what do you mean by electric field? Okay, thanks, Shivendra. That's a very, I must say, satisfactory definition. That's completely fine. In some sense, you can tell it's correct also. But a more, say you're not dealing with fluid. In a more generalized fashion, how can you define field? Alex, I am waiting for your response also. It's very interesting to know from an electrical guy what field means. Yes. So yeah, as you can both see, you have defined field based on your own understanding of the concepts or understanding of your concepts. But in general, if you that's fine, Shivendra. Exactly correct. I already said that your definition was correct. Both Alex and Shivendra, your definitions were correct. So what I exactly mean to say is that field, in a general way, could just be defined as a region or a space in which the effect of any physical entity or a physical force, I won't not say exactly force, but physical entity could be felt. Okay, your Shivendra described in terms of in terms of fluid mechanics, that your field is a place where movement of fluid is observed. Yeah, basically is a region where the movement of fluid is felt or experienced, right? Similar to that, Alex have defined that field is a place where the presence of magnetic effect can be seen. Exactly. If there is a charge and if the charge is experiencing a magnetic effect or a electrical attraction between other charge, you may say that that charge is in the within the electric field of the next other charge, right? It is feeling the effect of the other charge. That's why it is within the field of that or electric field of that particular charge, right? The effect is being felt in that region. That region is basically defined as field. Okay. So here we can also see that adhering to our definition, what we have discussed, we can see that in the case of our analysis, fluid mechanics, in our fluid flow analysis, we say that the length scale used in the measurement and analysis is large enough to be interacting with large number of molecules. It is then possible to talk of fluid as a continuous distribution of matter, and any fluid property may be expressed as a function of x and x, the three-dimensional space location, and possibly of time t. Okay, I guess this definition is very clear and properly relates the concept of field and fluid mechanics, which indeed are very much interrelated or correlated with each other. Okay, since you can see that we have discussed about particles, fluid particles, we discussed about the continuum hypothesis. So given that we the fluid particle fluid particle satisfies the requirement of the continuum hypothesis, the shape or the size or the dimension of fluid particle is in satisfies the continuum hypothesis, as well as just the fluid particle, the dimension of fluid particle satisfies the continuum hypothesis. We see that such fluid particles in a fluid flow domain would be interacting with various other fluid particles, right? Because they are all interconnected or connected by the help of some attractive forces. So these particles will be interacting with other flow particles, and since the fluid particles surrounding a certain particle would feel the effect of that particle, say the cohesive forces between those flow particles, the fluid particles, it will experience the cohesive forces between this between the other certain fluid particle will experience the cohesive forces because of other fluid particles surrounding it. You may say that these other fluid particles are in the field of a particular fluid particle, right? So and a similar explanation goes for all other fluid particles. So you may say that so you can clearly see that how we can implement the concept of field, or how the concept of field comes into picture when we are discussing with fluid and or more specifically the change of flow properties in a flow domain, and how the concept of field comes into picture, right? I hope it was clear. It's very simple. I hope I was clear in it. Given that the flow domain or the fluid particle that we have chosen satisfies the continuum hypothesis, okay, you will see, or you may read in some cases where the continuum hypothesis fails, right? Say in the case of rarefied flow dynamics, right? In rarefied flow dynamics or rarefied gas dynamics, it's more accurate. So in this case, in the study of rarefied gas dynamics, we observed that the flow particles are so far apart in these cases, and these are usually experienced in the or really experienced when the spacecrafts are in the outer space. So in that scenario, like just to clarify the concept, in this scenario or in this particular condition, the term rarefied itself means that like the flow particles are fluid particles are much apart. In this case, the gas particles are much more apart than in the case that it would have been in the case of a water, right? Compared to water, the gas particles are much more apart in this condition, in this scenario. Okay, when the concept or the physics of rarefied gas dynamics come into picture. So in that scenario, since these particles are so much far apart, they gradually tend to move out or move away or move away from the field of other particles. It basically means that they are so apart that they are not able to feel the presence of the other particles, right? So in that case, the continuum hypothesis breaks down, and all our governing equations that we're going to deal with fails while we're dealing with rarefied gas dynamics. So I hope I was clear. Okay. And again, since we are dealing with field, the flow properties, since we are feeling the flow properties, the particles feel the flow properties. These properties may change with space and as well as time, and or both. Okay. So these flow properties are function of both space and time. So if we are dealing with field, say the pressure field or velocity field in the case of fluid mechanics, these properties would be with obviously be a function of space, and also maybe a function of time. Okay. So in the case of steady flow, the dependence on time goes away, so it only becomes a function of space. But in general, in most of the fluid flow in our day-to-day life, we see that these flow properties, pressure and velocity, are function of both space and time. Okay. Now, in the very first words that we're discussing for today's session were the Eulerian and the Lagrangian approach. Okay, we are discussing about flow description, and we are told that we will be dealing with Eulerian and the Lagrangian approach. Eulerian and the Lagrangian approach. Sorry. Okay, so Lagrangian approach. Okay, so let me see what here. Okay, so could anyone of you from Alex, Shivendra and Prashant, could anyone one of you please explain me about the Lagrangian approach? See, because if I go on discussing about all the topics, I guess I will not be able to cover the content of this week. So I don't feel it's right that I go on discussing everything. I also expect that you may also tell or interact, so that both the time is saved, and at least I get to know that you have got a proper understanding of the course. So could anyone have please tell me about the Lagrangian approach of fluid description? Please feel free to speak up. Like writing, it may take time. Feel free to speak up. Alex, Shivendra, Prashant, any one of you, please. Funnily enough, the very definition of Lagrangian approach is being displayed on the screen right now. But still.
Hi, Abhishek.
Yes, sir.
I would request the students to ask questions, please, because you could listen to the lecture that I've already given. So if Abhishek is spending so much effort and so much time trying to explain this, the purpose of this is only to be be with him and keep on asking questions. Don't worry about how the questions sound. Just keep on asking questions. Thank you very much.
Thank you so much, sir. As you have listened to Professor Gupta, he insisted that you ask questions, or moreover, I anyway wanted this session to be interactive. So if I'm asking something, even though it's very lame that the very definition of Lagrangian approach is being displayed on the screen, it would be very fine if you just interact with me and just tell me like how you understand the concept. So that would be very helpful. Sure, Prasant. Yes. Yes, Prashant, you have raised your hand. Could you please tell?
Yes, sir. Sir, my question is from previous slide that the number, Knudsen number which define the whether it's a rarefied flow or a continuum flow. So, sir, what is the natural flow? What is we are dealing day-to-day life where continuum is exist and continuities exist. So we define that properties exist, whatever flow properties of fluids exist. But sir, what happened in this? If, for example, if we consider the any pipe flow where the some parameter is goes on decreasing or goes on increasing whatever manners, we are taking the equation. So in a gradual, that the pressure is goes on decreasing or sometimes it goes on increasing temperature like that. But sir, it is really happened, sir. In my mind, in the actually microscopic level, if we are consider that flow in a particular parameter should be on decreasing. So there might be any point within the that location, and there might be some changes, adverse changes might be there. Means not in a regular fashion. That's either decreasing or increasing. Maybe sometime up and down, sometime it decrease, sometime decrease. So we are putting just only equation and allowing the fluid to follow that equation in that our assumption. But it is really happened or how, sir?
Yes, that's a very, I must say, very curious question, or very interesting question. In must say, it seems you're very curious. See, regarding the flow equations or how, as you were mentioning about flow through pipe, we will eventually see or discuss how the mathematical equations or what kind of governing equations govern the flow through a pipe, right? And then you will see that it mathematically tells us or mathematically consolidates the fact that the pressure should decrease or there must be a negative pressure gradient so that the flow could occur in the forward direction. That's one point. But you are asking that whether these equations really are being followed or not. See, yes. See, as I mentioned, any physical phenomenon, say right now you may know about nuclear decay or say population growth. These all natural phenomena could be described with the help of some certain differential equations, right? Or mathematical model, as you say. Those mathematical models are basically some certain differential equations, okay? And I hope you know about the differential equations. Am I correct? You know about differential equations, right? Prashant?
Sir?
Yes. You know about differential equations, right? Differential equations.
Yes, sir.
Yes.
Continuity equation. Yeah, many equations are there, sir. Let us suppose consider continuity equation or.
Yes, that only. I am going to that. See, the thing is that while the subject of fluid mechanics was designed, right? So it was established or being, well understood that all the flow physics or entire fluid flow in the whole known universe could be described by the Navier-Stokes equation. One more point to it, it's not complete. Navier-Stokes equation, given that the fluid is Newtonian. Okay, it's not valid for Navier-Stokes is not valid for non-Newtonian fluids. Given that the fluid is Newtonian, okay, that's the foremost criterion that it needs to follow, okay, and a inertial. Okay, that's fine. Let's not discuss about that. For Newtonian fluid, the Navier-Stokes equation would govern all the flow physics for a Newtonian fluid. Okay, that is well established and well understood. And we have seen that, or we have observed that, say if you are dealing with pipe flow, and if we are now going to say simple pipe flow, fully developed pipe flow, and where we observe a parabolic velocity profile. Okay. So it will the velocity profile will be parabolic. So say if I am not wrong, u of r must be some function of no, sorry, would vary as 2 u naught 1 minus r square by capital R square, where capital R is the density radius of the pipe. I may be wrong with the first coefficient part, but okay. So this is the velocity profile. Okay, this velocity profile is being obtained after solving the Navier-Stokes equation for the pipe flow. Okay, and this is what is a very idealized case. Okay, we assume that the flow is fully developed. There are some certain assumptions that we made. The flow is fully developed. The flow is laminar, steady. So these are certain assumptions. Okay, and if there is a flow that may occur in our day-to-day life that is fully developed, laminar and steady, the velocity profile that we may find at any cross section of the pipe would be exactly like this. Okay, would exactly be like this, and that is bound to happen because it has a crude mathematical proof or analysis, but after which analytical expression that describes the velocity profile at a particular location of the pipe. But as you have mentioned that it may very well happen that the flow in our the pipe flow that we encounter in our day-to-day life may not be fully developed because of certain issues. They may not be fully developed, and in most of the cases the pipe flow are turbulent, not laminar. Certain part may be laminar, but after certain instance, because of the pipe roughness, it becomes turbulent, and it's bound that it will not be steady, right? And how it may occur? It may occur because of some various issues, right? Maybe the valve operation that we are doing, that the person who is operating that flow in through the pipe may not be in a steady manner, right? It may fluctuate, it may occur, and the pipe may have some dents or high roughness that may cause the flow to become turbulent. So this prerequisite of the flow being laminar is not satisfied. Steady to is very difficult to satisfy. So given that these scenarios are not satisfied, then this equation will not be valid. But the thing is that having a simplified model or simplified design of our complicated day-to-day problems, right, day-to-day life problems, and trying to solve those simple problems mathematically gives us an idea of how the flow properties may change from one portion of the pipe to other. See, even if the flow is turbulent, right, even if the flow velocity profile does not satisfy this expression, it is bound to happen that for the flow to occur, we must have a negative pressure gradient, no matter what. Okay, here basically means here if it is P1, P2, then P2 should be less than P1, so for the flow to occur in this direction. And it is you will see that this is being proved after solving the analytic expression for this simple pipe flow case. Okay, we did not go to the complicated day-to-day practical problem, but a simplified case gives us a conclusion that we must have a negative pressure gradient for the flow to occur forward. This is a very important outcome that is being satisfied for all the flows, no matter what the condition is satisfied or not. Okay, so this simplified problems or simplified way or simplified design of our day-to-day problems at least gives us an idea or a vague idea or understanding of how the flow properties may change or would show a certain pattern, given that we are dealing with the simplified version of that complicated problem. Is that fine?
Sir, got it, sir. But mostly my doubt is clear. Some doubt is still there, but sir, I will ask further.
Okay, sure, sure. And okay, I guess for the if I was not able to clarify it out completely, I apologize. I hope that for next session we may be able to discuss and clarify our doubts. So I'm extremely eager for those sessions. So kindly forgive me if I was not able to clarify your doubts. Okay, but I hope at least you are getting some idea why we are dealing with these governing equations, or how exactly it happens, or what's the importance of that. Yes. Okay.
Sir.
Oh, who is it? Okay. So. Okay. Okay then. So. Okay. So. Okay. So we are discussing about Lagrangian approach. So okay, since we are time bound, I must say I'll just briefly go to Lagrangian approach. So there are two approaches for understanding the fluid flow. Okay, the fluid flow, to at least get a mathematical understanding of fluid flow. Mathematicians have deduced two methods: the Lagrangian and the Eulerian approach, and both of them are, I must say, equally important in their relevance. But one of the properties, one of the methods finds what to say, vast application, at least for our course. Like for our course that we're mainly going to deal, we will mainly deal with one of the methods, and basically the Eulerian approach, because of its ease, or because of ease of implementation, and giving quite accurate results. Okay, we may not say that the Eulerian approach gives us exactly the correct results. It may be there may be the case as described, as asked by Prashant, that where Lagrangian approach might become necessary. Okay, so the Lagrangian approach basically means that we will follow. See, we know that the fluid flow is composed of various fluid particles. So now we say that we follow a crude manner where we will follow each and every particle and try to calculate or evaluate its respective flow properties. Right, as described here. We follow every fluid particle as it moves around, and describe its location, velocity, and other properties as it moves around. Okay, we follow each and every fluid particle in the domain, try to obtain the fluid properties at that particular of that fluid particle and in the domain, and then try to get a cumulative effect that each particles in the flow domain would have. See, this approach is highly accurate and highly beneficial if you are going to deal with the very small scale variation of the flow properties. But as you can clearly see, this is very difficult to be realized in our day-to-day life, right? We may not go and see or try to evaluate the flow properties by following each and every particle in the pipe flow, right? We just want to get the pressure at the two different locations, say of a pipe flow. Now if you are going to follow each and every particle to get that may become a very tedious job. So to tackle that, mathematicians developed a different approach that is called Eulerian approach, that we'll briefly discuss. But for right now, the Lagrangian approach, since properties are measured for each and every particle, so these properties are a function of only time. These functions are the properties of only time and the initial position. Okay. See, if we are going to evaluate the flow properties in the scope of the Lagrangian scope, then the flow properties would depend on the time as well as the initial position. Here the x0 denotes the initial position. Okay, initial position, not the space coordinate itself, but the initial position. So to tackle with the issues that we may encounter because of the difficulties in implementing the Lagrangian approach, the mathematicians came up with the Eulerian approach. Okay. So in this case, we focus our attention to a particular region in the flow domain, We focus our attention in a particular region in the flow domain and then see or observe the variation of the properties. Okay. And then evaluate the variation of the properties at those particular locations where we have defined our flow domain, where we have defined our region of observation, or in this case we in this scenario we define it as a control volume, okay, or a control volume approach. So the fluid properties are specified as functions of both space, points and time. Okay, that's the fundamental difference between the in a mathematical manner. The fundamental difference between the Eulerian and the Lagrangian approach is that the Lagrangian approach only depends on the time and the initial location of the particles. But in the case of Eulerian approach, the flow properties are the function of both the space coordinates and time. Okay, so here the properties are measured by probes at fixed locations. We define our location at which we want to measure our flow properties, and then we insert certain probes or measuring instruments to calculate or evaluate the flow properties at a particular locations where we want the calculation to be made. Okay, so I guess the basic definition or understanding of Eulerian and Lagrangian approach was clear. So, or in a more clearer fashion, since we have time, I would like to say, give an example. Say if there is a black box, say, and there is a flow occurring. So the Eulerian approach would be in a fashion that we define our control volume. Say, and if we want to measure, say, the net force that acts in the control volume, so what we would do is we measure our flow properties at the inlet in this location and the outlet. And how we will do that, there is some certain approach how we do that. We will discuss about it. Once we know the value of the properties at the inlet and the outlet, we basically then use those properties to evaluate the net force that acts in the control volume. Okay. But in the case of Lagrangian approach, what we will do is, let me zoom it in. We will follow each and every particle that enters this black box. Okay, each and every particle. Each and every particle will have its own orientation and direction of motion. Right. And each and every particle would insert certain force with respect to its orientation and direction of motion to this certain region, and then once we are able to calculate this effect of all the particles, then we try to find out then we take the summation of all these forces, then finally find out the net force that acts in this control volume. Okay, both approaches are correct and equally correct, but you can clearly see the tedious nature that follows by following the Lagrangian approach. How it may become so difficult if you are going to follow each and every particle. So I hope this example helped you to understand the clear difference between the Lagrangian and at least the qualitative difference between the Lagrangian and the Eulerian approach. Okay. See, again, let's discuss about time rate of change. I guess we discussed it in the initial phases, that one of the learning outcomes. As I mentioned, that the total derivative or the total rate of change of the property, which is defined as the material rate of change, or in other words, the total derivative of the flow property would be the summation of the local rate of change as well as the convective rate of change. Okay, the local rate of change basically means that how the flow property changes at that particular location with respect to time, and also how the convective rate of change basically tells us how the flow property may change as it traverses through the control. In this case, or in our understanding, how the flow property changes as it traverses through the control volume. Okay. So that is the basic definition or understanding of the time rate of change. Okay, so this in this case this expression only shows us the time rate of change along in one direction only with respect to the x coordinate. So if the flow is one dimensional, so the flow property only depends on the one of the space coordinates, so it just shows that it's only function of x. So if this function of x, y and z also, so it will have other derivative, space derivative with respect to other spatial coordinates as well. Okay, so this is one of the example that I guess Professor Gupta dealt with in the lectures. So I'll quickly go through it. I hope I will be able to clear if at all you have any doubt. Okay, so it is given that there is we want to find out the local rate of change of temperature. Okay, okay, we want to find the local rate of change. Say it. Okay, it's the initial. Okay, say Dehradun. Okay, we want to find the local rate of change at Dehradun. Because this is how it is done. Okay, and we are given that the speed of wind, the wind speed that traverses from Jhansi to Dehradun is around 30 km/h. Okay, and the air heats up at 1 degree Celsius per hour. Okay, no, I'm sorry, I was unclear. See, there may be a certain say take a certain point within this from Jhansi to Dehradun. Say if we take certain point within Jhansi to Dehradun, okay, and we say that we want to find the local rate of change of temperature at that particular point. Okay, and it is mentioned that the wind speed from Jhansi to Dehradun is say 30 km/h, and the air heats up at 1 degree Celsius per hour. The net rate of change of temperature at that particular point is given there is 1 degree Celsius per hour. Okay, and so the question is what is the rate of rise of temperature at Jhansi? Okay, we want to know what is the rate of rise of temperature at Jhansi. Okay, to find it we need to evaluate the total derivative, but here sorry not the total derivative, the local derivative at Jhansi. So here it is given that the net rate of change of temperature with respect to time is 1 degree Celsius per hour, but you may also see that the change of temperature is not only because of the local rate of change, but also because of the blowing of wind, right? Since the wind moves with certain velocity, this movement of wind also causes the change in the temperature. Okay, which is bound to happen because of say the convective effects. It is bound to happen. If you do heat transfer, you may encounter convection also as one of the important modes of heat transfer. So the movement of air also causes the change in will cause the change in temperature. Okay, so it's also necessary that we take into consideration the change in temperature because of the motion, because of the movement of wind, from the one location to another. Okay, that's why so dt by d so dou t by dou x will be given by 10 degrees Celsius, but that's basically being found as we take the temperature difference between Jhansi and Dehradun, so it will basically be 25 minus 15 by 500 kilometers. This is basically the distance between the two places, and it will basically be 10 by 500. Okay, and then since we also need to calculate the velocity, so it will be v dou t by dou x, so it will basically be 30 into 1 by 50. It will basically give us 0.6 degrees Celsius per hour. This is the rate of change of temperature because of the motion of the wind from Jhansi to Dehradun. Okay, so that's why the we know that the net rate of change is a summation of the local rate of change as well as the convective rate of change of temperature. So that's why the local rate of change of temperature will be given by the total rate of change of temperature. I'm sorry, here again the notation is mistaken here. Sorry. It will be the total rate of change of temperature dt by capital DT by dt minus v dou t by dou x. So 1 minus 0.6. So 0.4 degrees Celsius per hour is the local rate of change of temperature at Jhansi. Okay. So I hope it was clear. So in some sense, you may treat the complete derivative. This is basically the complete derivative. This is this notation as an operator. Okay, as a linear, not a linear, as a mathematical operator. So this would basically be given as d by dt would be equal to dou by dou t plus v dot del. Okay, where v is the velocity vector and delta denotes the nebula operator. Okay, this basically is the nebula operator. Okay, so this you can treat basically the total derivative as a mathematical operator. Okay, in the case of Eulerian approach. And so if we just change our the variable upon which our total derivative operates, we can find out various total rate of change of that particular property. Okay, in the previous case we were dealing with total rate of change of temperature. So now if you are dealing with the total rate of change of velocity, it will basically give us the acceleration, right? We know that the rate of change of velocity gives us acceleration. So if we now operate the complete derivative on velocity, we just operate this operator upon velocity. So we will get dou v by dou t plus v dot del v. Okay, and just keep in mind again that this v is the velocity vector. Okay, not the particular velocity component. It's not the y velocity component, but the total velocity vector. Okay, or which would basically be v is equal to u I cap plus v j cap plus w k cap. Okay, so again we were given one example in the class, so I'll just go through it. It's very simple. It's given that v is equal to ax I cap minus y j cap. It's basically a 2D velocity field. Okay, only x and y components. So the z component or the this w is equal to 0. Okay, the velocity along the z direction is 0. So we implement this expression here. We need to find the acceleration. So dou v by dou t plus v dot del v, then it is 0. Since you can see that the velocity components are not a function of time, so we can clearly see that the flow is steady. It will or the flow does not change. At least the the velocity does not change with time locally. Okay, the net acceleration that is being caused is because of the convective part. Okay, or I will give a certain example for that. It's just because of the variation of the flow property as it traverses through the control volume. Okay, the convective part results in the net acceleration. Okay, so sometimes like students make a mistake by seeing that since the velocity component here is not a function of time, they may say that net acceleration is equal to 0. Okay, this is completely correct if this velocity component that we have obtained was obtained through our Lagrangian approach. Okay, but since this is not being obtained through the since we are expecting that we need to find the acceleration in terms of Eulerian approach or control volume approach. Even though the velocity components are not a function of time, they are function of space, and since you will see that if this value is not equal to 0, there would be a net acceleration even if the velocity components are not a function of time. Okay, the convective acceleration will come into picture. So just expand this expression here. We'll just expand this expression here. So Vx dou Vx by dou x ik plus dou Vy dou Vy by dou y jk. Okay, so Vx is Ax, then dou Vx by dou x is equal to A, then Vy is minus Ay, then dou Vy by dou y is equal to minus y, right? Sorry, it's minus A, sorry, it's minus A. So just complete the expression, and then we get that the acceleration is a square xik plus yjk. So okay, so this is it, and then we discuss some different flow visualization methods, right? Or in this case we will be for visualizing the flow we will be dealing with three types of flow visualization methods. This with the help of path line, streak lines, and streamlines. Okay, so from Alex and Shivendra, could anyone of you please define streamline to me? What do you mean by streamline? Because definitions are written, I don't want to go through it once again. Could anyone of you please tell me about streamline? What do you mean by streamline? Alex, Shivendra, please. We are time bound, like we cannot wait for too long. Expect that you just at least even give a try to explain what you mean by streamlines, streak lines, and path lines. Okay. The very definitions may seem quite elementary, but the implications that it has on visualizing the flow, visualizing flow, or the flow field is very large. Or you may eventually see that what you were expecting the streamlines actually turned out to be streak lines that you usually see during flow visualization. You will eventually see that when we are clear with the very definitions of these different flow visualization techniques. So please, Alex, Shivendra, just give it a try. It's completely fine if you don't know. Just give it a try. What does streamline may be complicated if you're feeling that way. Just tell me what is path line. I guess the very word itself tells us what path line means. Okay. Okay, so I think it's completely fine, but since we're time bound, I will just go through definitions quite quickly because I don't want to emphasize upon it much. I guess it is expected that you go through the lectures thoroughly so that we can have some certain kind of discussions in the sessions, problem solving sessions, but I guess it's fine. Okay, so the a path line can be defined just as a path that the fluid follows in the flow domain as a function of time, right? For a certain time, like if you are following the fluid particle, say from time t equals 0 to t is equal to 5, the path followed by that particular fluid particle, okay, not different fluid particles, but that particular fluid particle from time t equal to 0 to t equal to 5 would be defined as a path line. Okay, so basically it means that if you are selecting a particular fluid particle, and if you are following this, and if it is in a certain flow, then it's bound to move along with the flow, right? So if you are following this the path followed by this particular fluid particle for certain time,
then this path that this fluid particle follows is known as path line. Okay, there's a very definition of it. So this is an example that was again discussed in the lectures. So given that this is a velocity field, v is equal to y I cap plus 3 by 4t j cap. This is the velocity field. Okay, so we know that y would be equal to, we know that y, since y is the u velocity component, we can say that u is equal to dx by dt. Okay, we know that. And again, the v velocity component, v is equal to dy by dt, right? So just write it. U, the x velocity component will be equal to dx by dt, and y velocity component, v would be equal to dy by dt. Okay, so basically we want to find a trajectory that the particle follows as a function of time. A single particle follows as a function of time. Okay, so to get those trajectory, we basically need the x and y coordinates, right, at different instances of time. And if we get the x and y coordinates at different instances of time, it basically gives us the path line, right, or the trajectory of the particle. That is a very definition of path line, and as you can clearly see, this is the Lagrangian approach of following the flow visualization, right? We are following a single particle, that's why it's a Lagrangian approach. So adhering to this definition that they have given here, dx by dt is equal to vx, dy by dt equals to vy. It basically means dx by dt is equal to y, and dy by dt is equal to 3 by 4t. Okay, then we integrate these two equations, these two differential equations. Then x equal to y dt plus c1. Then we basically get y is equal to 3 by 8 t square. Then we get then if we integrate this one, we get y is equal to 3 by 8 t square plus c2. Now since we have the value of y here, we substitute y in this expression, right? Then we get y is equal to 3 by 8 t square plus c2, then c1 will remain as an arbitrary constant. Then we will basically integrate it, so we get 1 by 8 t cube, 3 will be included in the denominator, right, if we integrate it, plus c2t plus c1. Okay, and this arbitrary constant could be found out by the initial conditions, or like if we know the initial position of the particle, then at say time equal to t equal to 0, then we are able to find out the value of these arbitrary constants. Okay, so and since there are two arbitrary constants here, we need to know the location of the particles at two different times, say t equal to 0, t equal to 0, or t equal to 5. Then once we know that, we are able to get the value of both the x and the y coordinates. Okay, then we go to streak lines. So okay, let me again go to definition. So a streak line through a space point A is defined as the locus of all the particles which have passed through the point A at any time between some starting time and current time. Okay, so actually that I initially told that, see, if we are not clear with the definitions, we may interchange the these different flow visualization techniques or lines with each other. Okay, so you may observe some certain flow visualization techniques, right, where by the use of dye or tracer particles that we usually see, like see if there is a certain stream of water, and there is a dye injected in it, here, and if the flow is, say the flow is laminar or okay, let me not restrict it to laminar. Say if you are just injecting a dye to the flow, we may see that this dye injects particles in the flow stream, and these particles then color the flow stream, that at least that gives us an idea of how the particles this fluid particles move in this given free stream, or how the particles will behave in the given free stream. Like this I have drawn for laminar, but if it is turbulent, you will see that there may be some curved paths, right? Curved paths, curved trajectory. So these are bound to open. So this visualization technique, many people may like sometimes confuse that these are streamlines, but actually these are streak lines. Okay, these are not path lines and not streamlines, but streak lines. Why? Because we are injecting particles at a particular point, say A, right? At a particular point A, and it is locus of all the particles that have passed through the point at any given time, any given starting time and current time, right? So we inject the particles at this particular point. So all these particles must have passed through this point A to reach to these different locations, right? And this dye or this dyed path that these particles generate is the streak line of that. It's the streak line of this flow field. Why? Because if I zoom it in, here, dye is injected here. It will initially inject one particle, then it will reach since the flow has some certain velocity, it will move forward and reach some certain distance too. Okay, the moment it reaches to, next particle is being inserted at same point A. Then as the time is increased, the first particle will reach the position 3 and the second particle will reach position 2. And similarly, these particles that were injected or inserted at point A move through the flow field as the time passes and create a trajectory or line or a trace in the stream that helps us or gives us an idea of how these particles would behave because of the motion or because of the motion of this stream, this fluid stream. Okay, this gives us an idea how these particles behave in this free stream, in this stream. Okay, not free stream exactly, in this stream. This stream may be laminar, so if this laminar, these particles would follow straight lines and move in a very organized manner. Okay, similarly, if this given stream is turbulent, these particles would follow various chaotic trajectories, curved chaotic trajectories, and thus it will give us an idea that the stream that we are encountering or the stream that we are trying to visualize is turbulent. Okay, so these are streak lines. Again, okay, before discussing this problem, I guess this was discussed in the class. We will just go through the definition of streamline. Okay, so similar to that, a streamline is actually an imaginary line. Okay, it's not something that we can actually visualize or we are able to visualize, but it is an imaginary line that gives us the velocity of the particle at that particular point at a particular instant of time. Okay, see, it's given that a streamline is a trajectory of the velocity field and the local velocity vectors are tangents to the streamline throughout. So it basically means that the streamlines, say this is a streamline and this is the fluid particle that we are visualizing, then this streamline will actually give us the direction of the velocity field of this particular particle. So it will basically give us the velocity components, right? Give us the y component and the x components, say u and v. So these streamlines are basically the trajectories or the trajectories of the velocity field for this particular fluid particle. Okay, since they give us the direction and the magnitude and the direction and magnitude of the velocity field for that particular fluid particle, again at a particular instant of time. Okay, at a particular instant of time. These are instantaneous flow visualization techniques. This is an instantaneous line that only gives us the velocity of that particular at that particular instant. Okay, not throughout the time, only at that particular instant. Okay, so that is also necessary. So, and okay, Prashant, you have raised hand.
Sir, whether the streamline can be three-dimensional or always happens in two-dimensional, because it is only shown in only 2D equation.
No. Streamline can be 3-dimensional. Okay, see, for only 2D, it is expressly mentioned that I mentioned it's for 2D flows, but streamline is a concept that can be extended to 3-dimension also, and all the flows that we usually encounter in our day-to-day life are 3D, right? So the concept of streamlines can very well be implemented to 3D flows, but it is important that we don't confuse streamlines with stream function. Okay, stream function is a concept that we'll eventually discuss in the following sessions. Stream function is a mathematical tool that we use to solve incompressible 2D flows. Okay, though in some fashion it may seem similar, but it is not. I request that you don't confuse yourself with streamline to stream functions. Okay.
Yes.
So basically in 3D, the equation of streamline would take this form. Okay, it would basically be dx by u is equal to dy by v is equal to dz by w. So this will be the equation of streamline. Is it fine?
Sir.
Okay, thank you. So again, just a few moments before I told that sometimes we might confuse, or we may confuse ourselves by with this. We may confuse ourselves with these three different lines. Okay, we may confuse streak line with streamline or streamline with path lines. It may occur, but it is very important that since now we know definitions, we don't confuse ourselves. Like if you are looking or visualizing a flow with the help of a die, we must know by the instant we see the die that it is a streak line instead of a streamline or path line. Okay, we are visualizing the flow with the help of streak lines. Okay, the experiment that Professor Osborne Reynolds did was that the flow that he visualized in that particular pipe by inserting die was where indeed streak lines and not streamlines. Okay, but it's important that for steady flows, path lines, streak lines and streamlines are identical. Okay, and steady flow is a concept that if we try to visualize in a physical manner, can only be realized in steady flows. In highly laminar flows. Okay, so if we are trying to visualize the flow in a very highly viscous fluid, say if you are trying to visualize the flow around a cylinder, say if you place a cylinder in a container, I'm just drawing a top view. Okay, say 3D manner, this is container here. If you place a cylinder here, and now you are moving a very highly viscous fluid through it. Okay, so you may observe certain flow patterns. Right? If we insert a die here, so you will see certain flow patterns. Okay, so if given that the viscosity is very high, so it's highly viscous fluid, and it is steady. Okay, steady. So if this is the condition, then this die that we eventually see as the certain discrete parts that help us visualize the flow are actually streak lines. But since the flow is steady, we may tell that these streak lines are indeed the streamlines as well for this particular flow field. Though in practice, streamlines are imaginary lines that cannot be visualized actually, but if the flow is steady, and in this case highly viscous, so that the laminar nature of the flow is preserved, then we can say that the streak lines that we are observing here, these are actually streak lines, the streak lines that we are observing here are indeed can indeed show us the streamlines of the flow field as well. Okay, so for streamlines, for the concept of streamline, we dealt with some I guess this example was again dealt in the class, but just I will go through it very fast. So we are given that find the equation of streamlines for the given velocity field. So V is, so the V is so the U velocity component is, X velocity component is x 3t plus 1, and the Y velocity component is 2y. Okay, just substitute it this U and V in this equation. So dy by dx is equal to Vy by Vx. So Vy is 2y and Vx is x 3t plus 1. And then just use the concept of separation of variables. So since we took take y in the denominator and take dx here. And if we, since I told that streamline is a visualization technique which is only valid for a particular instant of time. So a particular instant of time, t must be constant, right? We are just visualizing for a particular t. T is equal to say some certain value, or only that moment only the streamline can be visualized, or at least accepted to realized. Okay, it can be told that the streamlines can be visualized or seen. So in that case, it's only valid for a particular instant of time. So t is constant. So we take this term out of the integration, 3t plus 1 and 2 out of the integration, and then do the integration of dx by x. This is our variable. So we get that ln y is equal to 2 by 3t plus 1 ln x plus ln c1, some arbitrary constant, and then we just solve this natural logarithmic, or arrange this natural logarithmic terms, and then find that y is equal to cx to the power 2, cx to the power 2 by 3t plus 1. Okay, you are clear, right, why I have taken t out of the integration, right? Because streamlines are only valid for a particular instant of time. So at that particular instant of time, t would be a constant, right? Okay, so I guess that's fine. Then okay, this part, rotation, distortion, this part I won't go through extensively, because Professor Gupta has like very nicely explained through the help of proper diagrams and derivations how we obtain these expressions for the linear strain rate or the volumetric strain rate. So this I will not discuss. I request that if you have any doubt, please go back to the lectures and see how it is derived, or you can always follow some standard books. And in fact, there is a standard book by the same name by Professor Gupta. You can follow that book also. Okay, that's very good. You can follow that. So I will just go through the expression very fast, because I don't think it will be wise to discuss the derivations completely in this limited time. So for a linear strain rate along the x direction, is given by dou u by dou x, and if you are trying to find the volumetric strain rate, it is given by dou u by dou x plus dou u by dou y. Again, only for 2D. If you are telling if you want to extend the concept to 3D, there will be another term. That will obviously be dou w by dou z. Then since for incompressible flows, we can say that the volumetric strain rate, or the change of the flow particles, since they are incompressible, there will not be any change in the volume of the fluid particles, right? And if that's the case, then the volumetric strain rate would be equal to 0. That's why it's shown here that dou u by dou x plus dou u by dou x plus dou u by dou y is equal to 0. So and similarly in the case of 3D, it will basically be okay. For 3D, we again encounter this equation, or in some sense I can say that it is in fact a simplified expression for a more generalized form of the equation of the continuity equation or the mass conservation that will eventually deal in the when we're dealing with the integral forms of our conservation equations in the later part of the course. So we'll discuss about that. Okay. So again, for the rotation, expression of rotation is given by omega is equal to half of dou vx by dou v by dou x minus dou v by dou y. Again, so you will see that this actually is a fluid rotation is actually a vector, and it has different components, and it's one of the components. Okay, it's not the entire, it's only one of the components. So it basically would be omega z. Yes, sir? Yes, Prashant, do you want to ask something?
Sir, actually, my doubt is for the streamline and streak line.
Okay.
Sir, if we consider a streak line, means it has it may have many numbers of particles flowing or maintaining that streak line at particular instant of time, means for a particular interval of time, right?
Sure, yes.
So it means that each particle should be maintained the same streak line as the path line for this, because the path line is different for different particles.
Yes.
But if you consider any streak lines, it may have numerous particles following that streak line. So each particle will have same path line for that period of time when the streak line is same.
No,
My question is for some typical types, sir. Actually, I'm not able to explain that what I'm feeling, but in short, I'm just asking if you consider the streak line, for example, straight lines there.
Okay.
So we can say that there are a number of particles following that streak line for a particular time interval delta t. So when we are saying that for delta t is a one streak line, it means whether for delta t there are only one path line for every particle following that streak line.
Okay. I'm sorry, I just missed it. Can you repeat this last sentence?
Sir, no, suppose there are, for example, take 10 particles are following the streak line. Okay. One streak line, 10 particles.
Okay.
So when if it is correct, then whether is it sure then 10 particle have only path line for a particular streak line?
No, that's not the case, right? That's actually not the case.
Sir, that is a confusion.
Yes, that is not the case. That's not the case. It's not necessary that if let me try to explain. Say this is the trajectory that if this is the trajectory that the streak line is the 10 particles of your streak line is being following. Okay, this is a trajectory. So it is not necessary that the first particle that was injected here, so after a certain time it will reach here, right? It will reach at the top, at the rightmost part. So it is not necessary that this first particle that was injected, let me denote it, this 1, 2, 3, 4, say 4 particles right now. So it is absolutely not necessary that the path line of the first particle should coincide with, the path line of the second particle should coincide with the path line of the first particle. Okay, in the case of streak line, again, it is not necessary that the path line of the third particle should coincide with the path line of the first particle or the second particle. But I again told that this will occur. This scenario will occur only in the case when the flow is steady. Okay.
Yes, sir. For steady, it must be all lines should be in line. Means it should be single line.
Yes.
Yes, sir.
Yes.
That is correct, sir. But sir, when we are talking about a streak line, means there are many particles are following the same streak line because it is a locus of all points. We at a particular interval of time, that is maintaining the same line.
Yes.
So I understood that point, sir. But my second question, which I still confused, but when the individual particle has its own path line,
yes.
So the particle should be lies on that same line, for streak line for that particular interval of time. So
See-
how path line is deviated from that streak line?
Yes,
Not
yes.
getting.
Okay. Let me explain you that. So for that, in simple fashion, I may say that if the flow velocity is not that high, okay, not that very high, say it is. Let me go to a clear page. It will be good. Okay, let me explain it here. Okay, say if this is the your flow stream, okay, the stream where you want to visualize the flow, okay, and it is having a moderate Reynolds number, okay, not that high, not that low, okay, some moderate Reynolds number.
Sir.
And you're injecting the particle here, okay, particle 1, it moves, particle 2, sorry, particle 2, then it moves, okay. So for the initial period of time, okay, for the initial period of time, both the particles may follow, it is not explicitly necessary, but it may happen that since the Reynolds number is moderate, both of the particles for a certain instant of time, okay, for some instant of time may follow same trajectory, okay, may follow the same trajectory. It may overlap, but I'm not doing this so that you can see the difference. Say green is the particle 1 and red line is the path line of particle 2. It may happen that for the initial instant, some initial part of the flow, initial instant of time, the path line may the path line of the two particles may coincide with each other, okay.
Sir.
But you will eventually see that since as we move ahead, and since the flow has some slight, even if it's very slow, but it has some slight perturbations or disturbances that may deviate these particles from their initial trajectories, okay. So the particle 2 after certain instant of time may follow this path, and the particle 1 after certain instant of time will follow certain different path. It is bound to occur, and that's why when you insert a dye, you will see that it will follow, if it is in a moderate velocity, okay, not that high, not that low. If it is not that high, then you will see that you will see a certain single streak line for certain instant of time, and then you will see that this diffuses out, then you will just see a smoke of particles rather than a certain particular line. So what is happening there? Initially all the particles are following the same path, but because of some certain disturbances or perturbations, the small disturbances that are there within the stream, inherently in the stream, this causes the path lines of all the particles to deviate from the initial position, that initial path that they are following, and thus all the particles now follow some different trajectories that is different from the initial path that they are following, okay. And you will see that as the Reynolds number is increased, as the Reynolds number will increase, this uniform path or this straight path, that the distance of the length of the straight path that the particles follow gradually diminishes. So you will see that it is very highly high Reynolds number, the flow is moving with very high velocity. These particles will, after only very few instant of time, it will just try to deviate. It will follow some different trajectories. But still,
So then what is then a streak line in this diagram? When you are at a point where the four lines are imaging out that end point, so that means that there are many four path lines are coming out from that single point.
yes.
Okay.
Not exactly from the point of injection, but after traveling certain
so-
distance.
Yes, sir. No, not point of injection. At the point of the last point, that is the four lines. I can see here four lines. That is just green and blue lines. That points are the four lines are showing. That is the path line, sir.
Yes, in the not the path line actually. See, it is. See, you will not actually see this path line. You will not see these lines actually. It will actually be only single particle that follows the path. You will not be able to see these lines. Okay, I'm just showing you, but you will not be able to see these lines because it will be a smoke of particles. There will be a lot of particles here. You will just see smoke of particles here, not these lines. Okay, there will be smoke of particles here.
Can I help a little bit?
Sure, sir. Please, sir.
The person, I think,
Prashant, yes.
Sir, look at lecture 7 from 20 minutes 18 seconds onward. I think it's a very descriptive example given the difference between streamline and pathline.
Sir,
20 minutes 18 seconds onwards, about a couple of minutes. Yeah.
Sir.
Do it later. Yeah, okay.
Sir.
Thank you.
Okay, so I feel I might have explained in a bit wrong manner, so I apologize to both Professor Gupta and Prashant, but I tried my bit to explain.
Everything you were saying was correct, 100% correct, but somehow that figure that I have there at 2018 makes the things a little clearer of the difference between things.
Yes, sir. Actually, I was just going through the part of this chaotic nature of the particles of the flow, right? I was going in that manner, but I guess this difficult to understand. Yes, sir.
It talks about difference between steady and unsteady flows and how the pathline and streamline deviate in unsteady flow.
Yes, sir.
Yeah, correct.
Okay, so I guess Prashant, I guess you got the. I guess you follow the advice of Professor Gupta and just clarify the doubts. Okay, I guess I was not able to clarify it properly, but I hope you will be much clearer after viewing the lectures. Okay, so
Sure.
I feel we are out of time today. Unfortunately, we are not able to discuss much of some examples, but clearly you may understand that especially this portion of the course, these flow visualization techniques and the Euler and the Lagrangian approaches, these are mostly conceptual topics. The more you are clear in the concepts, the better better grasp you have on the subject. So I feel having a clear concept is much more important asset than being able to solve more problems regarding these topics. But certainly we may discuss some topics in the next session. But since we are out of time today, I guess it's difficult to deal with problems, and moreover, problems regarding these topics are mostly one word or definition type problems. Like you are asked to define you're given certain definitions and try to match with the definition of that certain concept with the correct definition. So this kind of problems usually comes, and some simple mathematical evaluations of if you are given the velocity field, then you are asked to find out a linear strain rate or a vorticity, like that. So volumetric strain rate or the distortion, that kind of thing. So I don't think that's much difficult, but still we are not able to deal with it. I guess next session, I guess I will start with the Reynolds transport theorem. It's a very important topic, so that's why it will take a bit time, because I think we may need to know the very importance of this topic, like why this Reynolds transport theorem is important. So I guess it will take a bit more time. So I feel I should not start it today. So I guess we can stop the session here today, sir. So thank you. So
Thank you, Abhishek.
yes, sir. Could you please wait, sir, for a few moments? Yeah, and other students, you may please leave. We will discuss with Professor Gupta for some certain things. So please, other students, Shivendran.
Thank you, sir.
Thank you so much, Prashant. You may leave. We meet you in the next session. Yes. Thank you.
Thanks.
Okay, Prashant, you may leave.
Sir.
You may leave.
Sir.
Yes.
Okay. Thank you, sir. Thank you.
Sure. Okay. Good evening, sir.
Good evening.
I
must congratulate you. You did a very good job.
Thank you so much, sir. I actually didn't expect that you will be joining the session. I was like, I saw your profile and I was like, is it any other student who is imitating you? So I was confused.
I joined it because I was curious of how things are going. There's a new feature in NPTEL, so I was just wondering how.
Oh, sure, sir. Like, thank you so much for attending. And please, sir, could you give any suggestions? How could I improve the sessions, sir? Please, sir.
Seriously, I don't think you should talk too much about theory.
Yes, sir. But like they are not interacting, sir. That's the issue. Like I don't know whether they understand it or not. Sir, they are not at all interacting.
Professor Abhishek, the students don't read anything, they're not listen to the lectures. I don't believe they're listening to the lectures.
Yes, sir.
That's a problem. It's not automatically come. You're doing a good job, very good job.
Okay, sir. Thank you so much, sir. And
If you can send me your email address somehow.
yes, sir. Should I write it in the chat box?
Pardon me?
Should I write it in the chat box here?
You just tell me what it is.
Okay, I will write it on the screen, sir. Just
All right, you take my email address.
oh, sure, sir. Please.
V for Vijay, G for Gupta, VG3162
Yes, sir.
at gmail.com.
Okay, gmail.com. Okay, sir. Should I text you or something?
Yeah, whatever.
Okay,
Yeah.
sure, sir.
Yeah.
Thank you so
Okay,
much, sir.
fine.
Thank you so much,
Good.
sir. Yes, sir.
Thank you.